Hello, good morning, everybody, and welcome to EyeWay presentation and technology overview. I would like to start with the general top-down description of the system. So let's start. Okay, so we are talking about AR glasses, and basically it has a few components. So it has the component which we do not develop, but is obviously very, very critical. It's a SLAM, and we are using third party, and we right now don't have a team to develop this. This is something that we rely on other manufacturers simply because you know, everybody is doing it, and probably we don't have a lot of added value. As you will see in a moment, we are focusing on other components, which are the graphical pipeline, the compute, the projection, the eye tracking, the optical relay, and then obviously projecting it to the eye. Okay, so basically when we talk, what we are going to cover today is these four components: compute, projection, eye tracking, optical relay. Okay, and if we are talking about the concept in a top-down approach, basically what we mean is that unlike everybody else who are doing this kind of concept, basically what you see is that whenever the eye is rotating, there is a different portion of beams that are going in. Basically, the current approach of all the technologies out there is that they have an expanded eye box. So wherever the eye is located, the light enters the pupil. Okay, and this is general classical approach. What is different about what we are doing, and this is very important to understand because this is the fundamental part. We steer the projection to the exit pupil of the projection system to the gaze direction, meaning that wherever the eye is rotating, the projection part moves together with the gaze. And this is fundamentally different. Wherever the eye is not located, there is no beam going into the eye. So that basically this is the fundamental difference, and everything else is based on the idea that we can do that, and the benefits that we get from the system is based on this approach. So the system basically tracks the gaze the gaze of the user, and it steers the projection accordingly. That's the fundamental part. This is the main difference of what EyeWay does in comparison to everybody else. Okay, and all the benefits that we are going to talk about in the next slides basically are relying on the fact that we can do that. And this is fundamentally different from everybody else. So now we are going to talk a little bit more into the top-down description of the system. We will first overview the whole system. Then in the next stage, we will go into all the sub-modules. And then we will come back to the top level, how these sub-modules interact between each other, okay? So on a high level concept, what we have is basically the laser RGB light sources that are combined and illuminate the MEMS mirror, which then creates an image and it goes into the gaze tracking technology. Again, please be mindful that this is a gaze tracking technology. This is not a normal eye tracker that just outputs the data. It's also something that shifts the eye box of the system. So this is a fundamentally different approach than anything else that is out there. And I will explain more about how it works in a moment. But this gaze tracking device is basically relaying light through the combiner optical relay, and then it goes into the eye. So this is the fundamental performance of the system. If we are looking at the block diagram of this, so what we have is basically a few components, and these few components are the compute unit that you can see here, okay? And this is the business logic, all the CPU, GPU parts that control the mechanism of all the projection system. Then we have the projection itself, and it is comprised of two projectors that are combined. We'll talk more about this in the next slides. And then we have the eye tracking module, which basically is the element that has the steering MEMS, the quasi-static ones, and the sensors that illuminate inside the eye. We'll talk more about this. We have the optical relay, and the part which we don't develop, but also is an important part, is the external world tracker. Just to know, small notice, this is the eye. This, wherever you see the eye, and this is the world, the outside scene, and basically you can see through the optical relay, the real world. It's a see-through system. Okay, very important. So this is how the block diagram of this approach, this technology looks like. So basically, we have the projection that is moving by the eye tracking MEMS mirrors and relayed to the eye. That's the fundamental principle of operation of the system. So these MEMS are steering the beam. These components have a MEMS inside that create the image. Okay, so it's two different families of the MEMS, if you will. Now, if we are talking about optical design, so it looks more or less like this. So without going into too much detail about how the optical design is made, basically most of it is reflective, most of it's mirrors, just a small amount of lenses on the way. But basically what we have is a projection element, and this is the RGB laser with the MEMS, and it scans the beam and so on. We have the eye tracking part, which has the lasers and the sensors and everything. And we have the optical relay, which is this part, okay? So this is another very important part, and right now we are using off-axis freeform and elements that are more or less spherical, but in the future we're thinking of using either extreme freeforms or volume holograms. So this part, which is the only large part, will be shrunk down quite significantly. The rest can be very, very small, extremely small. So let's talk a little bit about the projection. I would like to start by showing you a short movie that might be better explaining the logic behind what we are doing. So,
augmented reality is, most likely, the next step in computer evolution. But there are challenges to overcome before realistic and immersive imaging can be delivered. One of these is a small field of view of most current devices. Widening the field of view comes at a cost of degraded image quality. Our solution is to embed an effectively pixelless image in the central foveal area within a much wider peripheral image. Owing to the properties of human vision that will feel just like a sharp and wide image anywhere you look. And it can be done with currently available projecting technology and computing power.
okay, so basically that means what we are doing, we are projecting an image that is high resolution where you look, low resolution in the periphery. However, because it is something that you fixate only on where you look, as you can, what you can see is basically from this, it moves to this. This is the perception that you get, because your eye moves on constantly. So just to recap, because we have already discussed this, the foveal part is 1 arcminute in resolution. The periphery is significantly less, therefore it saves a lot of bandwidth for computation. The projection overview, basically what it shows is that we have an RGB laser which illuminates the MEMS mirror, very small resonant MEMS mirror, and we have another RGB laser with another MEMS mirror that is positioned on with an element that controls the divergence of the beam. Therefore, we are able to create varifocal experience for the foveal part. All that is controlled by the 4 subframe splitter, which is basically today's an FPGA. In the future, it will be an ASIC. And these images go into an optical relay that eventually come out to the eye tracking and the projection system in general. It is very important to understand that there is also a SLAM output and a SLAM input and also eye tracking, because we need to do late warping for very accurate image creation. And another very important, because it's laser projection, we have also a safety mechanism that makes sure that the laser power is not exceeding the limit, and also that the MEMS mirror is constantly moving, it's not stopping. So these are the very important also safety measurements, that everything has to be very accurate and very safe in any given moment. This, I think, is one very important chart. Basically, what you can see here is that when we are talking about the projection itself, so this is the resolution, the relative acuity of the eye. Okay, we have a few sources that all show that this is more or less the relative acuity, and this is the resolution that we project. This is the foveal part, the high resolution part, and this is the peripheral part. And as you can see, we are at higher acuity at any given field or any given eccentricity in reference to the field of view. You see it? So this is the peripheral part, this is the foveal part, this is the relative acuity here. This is basically the definition of resolution versus eccentricity in the field of view of the human being. Okay, so in the center you have very high resolution. This is 1 arcminute. The moment you go out, the resolution falls quite significantly. So if you normalize, this is what you get. And we are at any given point above even the most extreme or the most optimistic measurements that the literature has provided us. So this is more or less the situation that we assume that the human eye cannot have a better resolution than our system in general. The system itself, so it illuminates the laser scan. So we have, this is the retina of the eye. This is the pivot point. You can imagine that the beam is scanning and pivoting around this point. So it moves back and forth all the time, and it covers an area. And what you get basically is that this area is covered with low resolution, and this central part is covered with high resolution scan. So basically that means that here the laser spot is very, very small, and here is very, very relatively large, but still better than what the human eye optics allow us to see. So this is very important. If we are to discuss how the system looks optical wise, so if you remember the combined system, basically this is the projection, the RGB laser projector sitting here. It's relayed to the MEMS mirrors of the eye tracking, and then to the combiner optics. So this is the combiner optics. Here is the eye. It's looking through this element, and you see the world. A little bit about the principles and the performance. So basically, we have 2 RGB projectors, one for the foveal, one for the periphery. They are running right now at 60 frames per second each. So, and in the future, we will double that frequency. The perceived resolution is 5K image. The reality is unobstructed simply because you know, it's just a piece of glass, and it's very large in reference to, and so it's just like your normal glasses. You know, your normal glasses do not obstruct the reality at all. It provides human vision resolution. The 1 arc minute is very, very important. It has a basic world tracking, or what we're using right now. And another very important part is that because it's laser scanning, we can change the information of what we are presenting on the fly. and it takes 0.2 milliseconds to change from bit to photon, meaning that this number, the 60 frames, is basically meaningless in this system. What is important is this number. This is the time to change the content of the frame. It's extremely fast. It's equivalent to a system that has 500 frames a second, basically. So this is more or less what we are, oh, sorry, 5,000 frames a second. So this was the projection. Now regarding the eye tracking. Eye tracking principle, basically, it's laser-based eye tracking. It determines the position of the eye in 5 degrees of freedom, and it doesn't require calibration per user. So there is a procedure to align and calibrate the eye tracker in the manufacturing phase, but for user, it's effortless. And you know, it's very important for us as consumers that there will be minimum frustration for use. That means that you don't waste your time in unnecessary procedures. So because it's calibration-less, we believe that it is much more less frustrating than any other eye tracker that there is out there. Okay, let's show you another short movie about how the eye tracker operates.
Most current eye tracking systems work by detecting the light reflecting from the surface of the eye. This technique requires computationally heavy image processing, causing low accuracy and high latency. Our solution utilizes infrared light scattering from the retina and back illumination of the pupil, essentially converting the eye to a flashlight. This method allows us to track gaze direction by following the optical axis of the eye. Our technique does not require image processing and therefore is much faster and more accurate. Our team at EyeWay Vision has built a functional prototype that is ready for miniaturization.
So yeah, let's continue. So regarding the eye tracking, so the eye tracking, basically it is on axis, foveal project, meaning that it illuminates the eye, it goes inside the pupil, goes inside and scatters from the retina. It has a simple photo detector, so it's a photodiode, and it tracks the eye motion as fast as the eye moves, simply because we use very small MEMS mirrors, which almost do not have any inertia. So and it is very low latency, simply because it doesn't have to do the processing, anything else. So basically, we do not use cameras, we do not do any image processing, and therefore it's very low power consumption, and it is eye safe. For the eye tracking operation mode, what we use, as I mentioned, it is an IR laser that goes inside the eye. It's scattered there. It backs illuminates the pupil, and we use a photodiode to track the position. And the system basically minimizes the error. It maintains the center and the perpendicularity to the pupil. Okay, that's the optical performance of the system. To demonstrate a little bit more how it operates, basically what we have is the eye. Just a moment, I'll try to add the pointer. So we have these two mirrors, and these two mirrors, basically what they do, they shift the incident beam that goes inside and the reflected beam, so it will be retraced or be coaxial with itself. Therefore, it's always going inside the eye in the same position. So this is a fundamental method of tracking the eye. So it's not a corneal based, it's a retinal based tracker. Okay, it is very unique and it is very fast, and we do not need to be affected by any ambient situation. Basically, this system is allowing us to be completely decoupled from the fact that we are illuminating different kind of eyes. As long as it is a human eye, we will be able to track it. For the block diagram, so what we have is basically these are the, sorry, I'll start here. This is the IR laser. It goes into the system through the two actuated mirrors, then the optical relay, and goes into the eye. The light that is scattered inside the eye is going back through the same mirrors, and it's going to these two position sensors. The two position sensors are required because we need to know the lateral and the angular position of the eye. So that means that we need at least 4 degrees of freedom. So this is why we have two position sensors. Now everything is going into the eye tracker control. Basically, right now it's a microcontroller. From this, basically, we have the main CPU which runs the model and everything that basically is calculating together with a SLAM the relative position of each and every object in space in reference to the eye. Obviously, we have the power and the safety. And because this system is very fast and the projection is very fast, we have a fast channel going to the rendering pipeline, basically to the projection unit. Okay. As optics go, so for this is the same optical relay. And then these are the two MEMS mirrors. And then these are the laser and the sensors. Basically, there are two of them. This is one, and this is the other. So this is common part. What is different is this part. Basically, the other one is coming from here. That's the combiner. This is the surface of the combiner that you see here. And the reason is that, as I mentioned, we need to measure 4 degrees of freedom. So again, all that can be very, very small. Basically, it can be wafer level components. It can become millimeters in size. Obviously, right now, these components are lab components. So they are relatively large, but there is no limitation of how small they can be. Regarding the eye tracking performance of spec, so the latency, and the latency is a very problematic term because we never actually lose the eye. There is no latency as in other system, but this is more of an inertia of the MEMS. It's less than 2.5 milliseconds. The accuracy is better than 1/10 of a degree. The sampling rate of the system is 16 kilohertz, or it can be pushed even further, but we don't see any reason for this. We do not have any ambient light issues. We have modulated signals, so it's very, very robust to any other interference in the environment. The angular track range is plus minus 15 degrees. The lateral track range is plus minus 1 millimeter after the initial alignment, obviously. So you align the device, and then you have these parameters. So now back to the combined system, just to remind us what we have is the projection unit that projects the two images, the foveal and the peripheral. They go into the eye tracking, and then the optical relay, and then into the eye. Now the eye tracking part is going also into the eye. This is the infrared laser, and it is coming back and measuring the reflection from the eye. So this all works in synergy. I will show you in a moment a short video clip how it operates. So if we look, so basically, just a moment, maybe I'll switch back to the pointer so you'll see. These are the eyes of the user's eyes. They are tracked. What you see here, this red or green small rectangle is the foveal part. The large rectangles are the peripheral part. They are moving together with the gaze. So they are locked to the eye, to each eye separately, because we have eye tracking for each eye separately. And you will see how it performs. Now, another part which we didn't talk in depth, but basically we have also the varifocal part. So it changes the focal distance also according to the object that is observed in any given distance. So now let's go back to the movie. Let's see. So basically, this is the main mode of operation. We have according to where the fixation is, the objects are tracked, or the eyes actually are tracked. This is let's assume that this is a virtual object. So whenever it comes, you can see that this is the high resolution part and this is the periphery. When we are thinking about it in an environment, so you will see in a moment. So these are the parts of the environment, high resolution and low resolution part. And then when the user is looking here, now this is a high resolution part and this is the low resolution part. So it really depends where the user is fixating. This would be the experience that the user will, what we are going to project. Obviously for the user, it will feel just like a natural world, because the low resolution part will be outside of the field of view of the user. But this is the total experience. Okay, let's go back to this. And now just to recap this part, basically what you see is that this is the foveal part, this is the peripheral part. Let's say this is 100% overlap, and then according to the focal plane, it will be moving and changing its overlap, because it's really if the object is here, obviously we will need to overlap these fields somewhere here. But basically, this is the fundamental performance of the system. And this is why it's much better, because it's adaptable to the user. Basically, this high resolution and the low resolution part. Again, the peripheral can be as large as we want, basically, as the optics allow us. Now, if I go back, so for the transmitted data, this would be the experience. So you can see that Mingwei that is moving here, she's in high resolution, and the periphery is in low. But if you follow her, you will always consider everything to be in a normal, adequate resolution. Basically, it's good enough. So this is more or less the explanation of how it operates. Okay, so basically now let's talk a little bit about the graphical pipeline, because obviously this is very important. Now, it's very important to understand. So the graphical pipeline, basically 1/3 of the company is software team, software and algorithms, meaning that we are developing our own drivers, mid-level software, plugins for Unity and Unreal, all the low-level porting to. Right now we are porting mostly to NVIDIA GPUs, but in the future we will obviously port to Qualcomm and other GPUs that are mobile. And the fundamental idea is that we have the most optimal graphical pipeline to present to create an image in the most efficient, most power and latency efficient way. So to explain a little bit about the graphical pipeline, basically what we have is in the interfaces such as wireless communication, commercially available SLAM. We have all the eye tracking elements, the MEMS and the sensors, and the GPU and the CPU that are relevant for these parts. We have the projection engine, which gets its data from the business logic machine. And business logic machine, it can be any device that basically is the part that we are using at the moment. And at the moment we use a PC, Windows running PC with an NVIDIA GPU. In the future, it will be a mobile platform, probably with Qualcomm processor. But basically, what we have is we are synchronized to the projectors with horizontal and vertical sync. So we send data specifically for each projector in the most efficient way for this specific projector. And then we are sending also the video data. So we have 4 SVGA video streams. And another parameter that we also send is the Z buffer, which basically means at which distance we would like to create the image. So it operates the varifocal part of the projection. So this is more or less the graphical pipeline and the data flow. Obviously, there are much more in detail descriptions about how things work for the graphical pipeline. As I mentioned, 1/3 of the company is basically focused on software development. However, this is very proprietary data. So to talk a little bit about the system specifications, and this is more or less where we are shooting for the first AR product. So we are talking about head-worn system. We are talking at the first stage, it will be 2 RGB laser projectors per eye. In the future, it will be reduced to 1 more complex or more efficient projector per eye that will be able to do the foveal and the peripheral projection. The angular foveal resolution is 1 arc minute. For the peripheral, it should be better than 10 arc minute. Right now, we are shooting for 8 arc minute. The brightness range is between 0.01 to 20,000 nits. And the laser dynamic range is 8 to 10 beats. It depends on various aspects and what is required. But basically, we are shooting for photorealistic images. The instantaneous field of view diagonal would be around 70 degrees. And since we have an eye tracker with another plus minus 15 or 30 degree cone, we're talking about 100 degrees overall field of view. Now the displacements of the headset should be less or around 1 millimeter. We obviously can trade off between the 15 degrees eye tracking and the 1 millimeter. We can do, let's say, 7 degrees eye tracking, and then we can say, okay, plus minus 5 millimeters or something like this. Now, the accommodation we will be doing from infinity, which is 0 diopters, to 5 diopters, which is 20 centimeters away, plus the prescription. So anyone that has a prescription of whichever number plus, if needed, we are able to introduce also the cylindrical element to compensate for any astigmatism that the user has. And obviously, we are able to do the varifocal part. And the form factor that we are shooting for is wearable glasses. Glasses meaning not a headset that is large and helmet-like. So this is very important also. For the power consumption, what we have is basically for the power consumption of the electro-optics, meaning the lasers and the MEMS and all these elements. We're talking about 1.2 watts. For the connectivity, for the connectivity, it's around 0.4 watts. And for the computing and processing and everything else is around 3.3 watts. This is more or less the overview of the system and how it operates.